Let me start with something that sounds almost ridiculous. Right now, as you sit there reading or listening to this, you are moving faster than a bullet. A typical rifle bullet travels at around 3,000 kilometers per hour. The Earth at the equator spins at about 1,670 kilometers per hour. That alone is already fast enough to make you uneasy. But that's just the beginning. The Earth also orbits the Sun at about 107,000 kilometers per hour. And our entire solar system is circling the center of the Milky Way at roughly 28,000 kilometers per hour. Add these motions together, and you are flying through space at extraordinary speed. And yet, you feel absolutely nothing. Your coffee isn't sliding across the table. Your hair isn't blown backward by some cosmic wind. You don't feel pressed against the western wall of your house as the Earth spins eastward. Everything feels calm, stable, motionless. So something about our intuition must be wrong. When most people think about motion, they imagine something moving through something else. A car moves through air. A swimmer moves through water. A bullet tears through the atmosphere. Motion in everyday life is associated with resistance, with wind in your face, vibration in your seat, or the rumble of an engine. But what if motion doesn't actually require any of that? Imagine you are inside a very smooth airplane flying at 900 kilometers per hour. The windows are closed. The ride is steady. You toss a ball straight up. Where does it land? Back in your hand. It does not fly toward the back of the cabin. Why? Because before you even threw it, the ball was already moving at 900 kilometers per hour along with you in the airplane. When you tossed it upward, you only changed its motion vertically. Horizontally, it kept moving forward at the same speed as everything else inside the plane. To you, inside that system, the ball appears to go straight up and straight down. Now imagine the airplane has no windows. It moves perfectly smoothly. There is no turbulence, no engine vibration, no sound from outside. Could you perform any experiment inside that sealed cabin to determine whether you are moving at constant speed or sitting still on a runway? The surprising answer is no. This was one of the great insights of Galileo Galilei. He imagined being inside the cabin of a smoothly sailing ship. Fish swim in a bowl. Water drips from a bottle. Insects fly around. Everything behaves exactly the same whether the ship is moving steadily or at rest. That idea is deeply uncomfortable to human intuition. We instinctively believe that moving should feel different from not moving. But nature does not work that way. Motion at constant speed is invisible from the inside. Only changes in motion announce themselves. And this is the first crack in our common sense understanding of reality. The Earth feels still not because it isn't moving. It feels still because the air, the oceans, the mountains, and everything around you are moving together. There is something even more subtle hiding underneath all of this. Your body does not actually detect speed. It detects acceleration. That distinction sounds technical, but it is deeply human. You have experienced it your entire life. Imagine you are sitting in a car at a red light. The car begins to move forward. In that moment when it starts rolling, you feel pushed back into your seat. A few seconds later, the car reaches a steady speed. Now the pushing sensation disappears. You are still moving, perhaps very fast, but you no longer feel anything unusual. Then the driver hits the brakes. Suddenly you lurch forward. Or the car takes a sharp turn and you feel thrown sideways. In every case, what you felt was not speed itself. It was a change in speed or a change in direction. That is acceleration. This idea was made precise by Isaac Newton. His laws of motion tell us that forces cause acceleration, not motion, not velocity, acceleration. A constant velocity requires no force at all. Once something is moving steadily, it will continue moving steadily unless something changes it. That is already strange enough. But now apply it to the Earth. The Earth rotates at a nearly constant rate. It completes one full turn every 24 hours with astonishing regularity. There is no sudden speeding up or slowing down. There is no jerking motion. It is smooth and continuous. The Earth also orbits the Sun at a nearly constant speed. It does not abruptly change direction. It follows a gentle curve through space, held in orbit by gravity. From your body's perspective, nothing dramatic is happening. There is no sudden acceleration, no jolt. But wait, you might say, isn't moving in a circle a kind of acceleration? Yes, it is. Even if your speed stays the same, changing direction counts as acceleration. If you tie a ball to a string and whirl it around your head, the ball is constantly changing direction. Something must pull it inward to keep it moving in a circle. That inward pull is called centripetal acceleration. So the Earth's rotation and its orbit around the Sun do involve acceleration. The key is scale. The rotational acceleration you experience from Earth's spin is tiny. It slightly reduces your weight at the equator by about 0.3%. That's measurable with precise instruments, but it's far too small for your nervous system to notice. Your inner ear is sensitive, but not that sensitive. Similarly, the acceleration from Earth's orbit around the Sun is spread out over an enormous circular path. The change in direction each second is extremely small. There is no sharp turn, no sudden curve. It is a vast, gentle arc through space. Your body evolved to detect immediate threats, stumbling, falling, being thrown. It did not evolve to sense the subtle curvature of a planet's path around a star. So you do feel Earth's motion, but only in the faintest possible way, buried beneath gravity and the ordinary forces of daily life. What you call stillness is actually motion so smooth, so steady, and so shared by everything around you that your senses cannot distinguish it from rest. And that realization forces us to admit something profound. Our direct experience is not a reliable guide to the structure of the universe. Now let's deal with a very natural objection. If the Earth is spinning at more than 1,000 kilometers per hour, why don't we feel a constant, violent wind blasting from east to west? Why isn't the atmosphere left behind as the planet rotates underneath it? This question seems so obvious that for centuries it was used as an argument against a rotating Earth. The answer is simple in principle, but subtle in implication. The air moves with the Earth. Gravity holds the atmosphere close to the planet. But more than that, the air already shares the Earth's motion. Just like the ball inside the airplane was already moving forward before you tossed it upward. The air around you is already rotating along with the ground beneath your feet. To see why this matters, imagine a giant glass sphere enclosing a small world inside it. The sphere rotates steadily. Inside there are oceans, clouds, birds flying, trees swaying. Everything inside that sphere shares the rotation. If you stand on the surface and jump, you land in the same spot. The air doesn't rush past you at extreme speed because it is part of the same rotating system. There is no reason for the atmosphere to remain stationary while the Earth spins. Stationary relative to what? That question is the trap. We instinctively imagine some invisible, fixed background in space, like a stage, and we picture the Earth spinning against it. If that were true, perhaps the air would lag behind. But space is not like a solid surface you can scrape against. There is no cosmic wall creating friction as Earth turns. Instead, the Earth and its atmosphere formed together from the same rotating cloud of gas and dust billions of years ago. The material that became the planet was already spinning. The material that became the atmosphere was part of that same motion. Nothing needed to catch up. Of course, the atmosphere does not rotate perfectly in sync everywhere. There are winds. There are jet streams. There are storms. And here something fascinating appears. Because the Earth rotates, moving air does not travel in straight lines across its surface. Its path curves. This is due to what physicists call the Coriolis effect. It isn't a force in the usual sense. It's a consequence of describing motion within a rotating frame of reference. In the northern hemisphere, large-scale air currents curve to the right. In the southern hemisphere, they curve to the left. That is why hurricanes spin in opposite directions, depending on which side of the equator they form. So the Earth's rotation is not hidden. It reveals itself in subtle, global patterns. But those effects are indirect. You don't feel the Coriolis effect in your muscles when you stand up. You don't sense the curvature of atmospheric motion when you pour a cup of coffee. The scale is too large. The processes are too slow relative to your body. And here again, we confront a limitation of intuition. We tend to think that if something is happening at enormous speed, it must produce enormous sensation. But speed by itself is not the issue. What matters is relative motion, motion between things that interact. You and the air are not racing past each other at 600 kilometers per hour. You are moving together. The relative speed between you and the air in your room is close to zero. And that is the only speed that your skin, your lungs, and your senses can detect. So the great spinning of the Earth is not absent. It is woven into the behavior of oceans and skies. It shapes climate and weather. It determines the rhythm of day and night. But because you are embedded inside that rotating system sharing its motion at every moment, it feels like stillness. What seems like stability is actually participation in a vast, coordinated motion too large for your senses to isolate. Now we arrive at a subtle but very important point. Earlier, we said you only feel acceleration, not constant speed. But the Earth is not just gliding in a straight line. It is spinning. It is orbiting the sun. And both of those are forms of acceleration because the direction of motion is constantly changing. So why don't you feel that? Take something simple. Tie a small weight to a string and swing it in a circle around your hand. Even if you keep the speed constant, you feel a pull on the strings. That pull is necessary to bend the path of the weight into a circle. Without that inward pull, the weight would fly off in a straight line. That inward pull corresponds to what physicists call centripetal acceleration. An object moving in a circle is always accelerating toward the center of that circle, even if its speed never changes. Now consider the Earth's rotation. At the equator, you are traveling in a circle with a radius of about 6,371 kilometers. You complete that circle once every 24 hours. That means you are constantly being accelerated inward toward the center of the Earth. You might expect to feel that. In fact, you do, but in a disguised way. The inward acceleration required for circular motion is provided by gravity. Gravity pulls you toward the center of the Earth. Most of that pull simply keeps you standing on the ground. A very tiny fraction of it is oozed to bend your path into a circle as the Earth rotates. Because of this rotation, you actually weigh slightly less at the equator than you would if the Earth were not spinning. The outward tendency from the rotation partially offsets gravity. The difference is small, about 0.3%, but it is real and measurable. So the rotation is not something your body completely ignores. It is built into what you experience as your weight. Now think about Earth's orbit around the Sun. The radius of that orbit is about 150 million kilometers. The time to complete one revolution is 1 year. That is an enormous circle. The curvature is incredibly gentle. The inward acceleration toward the Sun is much weaker than the gravity holding you to Earth. In fact, the Sun's gravitational pull on you is almost completely canceled out by the fact that you and the Earth are falling toward the Sun together. You are in what physicists call free fall around the Sun. This is a strange idea. The Earth is not being held up in its orbit. It is constantly falling toward the Sun, but moving sideways fast enough to keep missing it. You, standing on Earth, are participating in that same fall. And yet you do not feel like you are falling. This brings us to one of the deepest insights in physics, later refined by Albert Einstein. He realized that being in free fall feels like weightlessness. If you were inside a falling elevator, ignoring air resistance, you would float. The gravitational pull would still exist, but you and the elevator would accelerate together. In orbit around the Sun, the Earth and everything on it share the same acceleration. There is no internal strain, no stretching, no differential force large enough for your nerves to detect. So yes, you are accelerating through space right now in multiple ways. But those accelerations are either extremely small or shared uniformly by everything around you. What you interpret as stillness is actually a carefully balanced combination of gravitational forces and circular motion. The acceleration is there, but it is either too small or too evenly distributed to produce the dramatic sensations your body associates with movement. And once again, we see that our direct experience hides as much as it reveals. Let's push this even further with a thought experiment. Imagine you are floating in deep space, far from any stars or planets. There is no visible light, no nearby objects. You are inside a perfectly sealed box with smooth walls. The box contains some simple equipment, a ball, a flashlight, maybe a small clock. Now suppose the box is drifting at 100,000 kilometers per hour in a straight line. Could you tell? You might try tossing the ball upward. It falls straight back down into your hand. You shine the flashlight across the box. The beam travels straight. You set the clock on the wall. It ticks normally. Nothing inside behaves strangely. Now suppose instead that the box is completely at rest relative to distant galaxies. Every experiment gives you exactly the same result. There is no internal test that can distinguish between moving very fast at constant velocity and not moving at all. That idea is deeply counterintuitive. It feels as if speed should be something absolute, something you either have or don't have. But in physics, speed only makes sense relative to something else. This insight was sharpened dramatically by Albert Einstein in his theory of special relativity. He took the principle seriously. The laws of physics are the same in all inertial frames, that is, in all frames moving at constant velocity relative to one another. If you are in a smoothly moving spaceship with no windows, you cannot perform any experiment to detect your constant motion. The physics inside does not change. That means there is no universal label in the universe that says, this frame is truly at rest. For centuries, physicists imagined something called the orbital, a kind of invisible cosmic substance that filled space and provided a background against which motion could be measured. The Earth, they thought, must be moving through this ether, but experiments failed to detect it. No matter how carefully scientists looked, they could not find evidence of a preferred state of rest. The universe did not cooperate with that assumption, so the idea was abandoned. This is one of the hardest conceptual shifts in science. We naturally think there must be some ultimate stationary backdrop. After all, in everyday life, the ground feels like that backdrop. When you walk, you move relative to the Earth. When a car drives by, it moves relative to the road. But the Earth itself is not resting on anything. It is not sitting on a platform in space. It is simply moving relative to other objects, the sun, distant stars, other galaxies. And those objects are moving too. You might say, fine. But surely we can define motion relative to the entire universe. In a limited sense, we can measure motion relative to large-scale structures like the faint afterglow of the Big Bang radiation that fills space. But even that does not provide a fundamental, absolute stillness written into the laws of physics. It is just another reference. The deeper lesson is this: motion is not something an object possesses by itself. It is a relationship between objects. When you ask, why don't I feel Earth moving? You are quietly assuming there is some absolute standard of rest you could feel yourself deviating from. But if all motion is relative, then there is nothing special about Earth's state of motion that your body could compare against. You feel stationary because, in your frame of reference, the Earth's surface, you are stationary, and that statement is not an illusion. It is as valid as saying Earth moves around the sun. Both are descriptions from different frames. What changes is not reality, but perspective. And that realization quietly dismantles the idea that there is a single, privileged way the universe must be described. Now let's slow down and ask a more careful question. When we say the Earth moves at 107,000 kilometers per hour around the sun, what does that actually mean? It means that relative to the sun, the Earth changes position by 107,000 kilometers every hour. But relative to you sitting in your chair, how fast is the Earth moving? 0. That sounds like a trick, but it isn't. It's a precise statement about frames of reference. In your everyday frame, the Earth's surface, you are at rest. Your coffee cup is at rest. The walls are at rest. The air in the room is approximately at rest. The fact that this entire system is moving relative to the sun is true, but it does not contradict your local stillness. This is where language begins to mislead us. When someone says, you are moving faster than a bullet, it sounds dramatic because we instinctively imagine motion as something absolute. We imagine a cosmic speedometer somewhere in space measuring how fast we are really going. But there is no such device built into the universe. Speed is always measured relative to something else. A bullet moving at 3,000 kilometers per hour is moving that fast relative to the gun, or the ground, or the air. But relative to someone riding alongside the bullet at exactly the same speed, the bullet would appear motionless. That sounds absurd, but it's correct. If you were somehow flying perfectly alongside a bullet at the same speed and direction, you could reach out and hold it gently. In your shared frame, it would not be racing forward. It would be at rest. This is the core difficulty for human intuition. We evolved in a world where the Earth seemed fixed and everything else moved against it. The ground felt like a natural reference frame. So we quietly absorbed the assumption that rest means rest relative to the Earth. Physics slowly dismantled that assumption. When we compare Earth speed to a bullet's speed, we are mixing frames. The bullet's speed is usually measured relative to the ground. Earth's orbital speed is measured relative to the sun. These are different reference points. It's like saying, this car is faster than that airplane, when one speed is measured relative to the highway and the other relative to the air. Without a common reference, the comparison loses meaning. Even statements about the solar system moving around the center of the Milky Way are relative. We measure that motion relative to the galaxy's center, which we infer from gravitational effects and the motion of stars. But the galaxy itself moves relative to other galaxies. There is no final anchor point. This is deeply unsettling because the human mind craves foundations. We like the idea of a fixed background, a stage on which events unfold. But modern physics tells us there is no universal stage floor labeled, truly at rest. Instead, there are countless valid perspectives. From the sun's frame, Earth moves in an ellipse. From Earth's frame, the sun appears to circle us once per day and shift slowly through the seasons. Both descriptions can be made precise. Neither is more real in an absolute sense. One is simply more convenient for certain calculations. So when you ask why you don't feel the Earth's enormous speed, the answer is not that the speed is fake. It's that speed is relational. Relative to your surroundings, you are not moving at all. And your body, your senses, and your intuition evolved to operate within that local frame, not within the vast, shifting web of cosmic relationships that physics eventually uncovered. Now we come to an uncomfortable boundary between what we know with confidence and what remains open. We know the Earth rotates. We can measure it with gyroscopes, with satellites, with the way distant stars appear to move across the sky. We know the Earth orbits the sun because we can track planetary motion with extraordinary precision. We know the solar system moves within the Milky Way because we observe the motion of nearby stars and measure galactic rotation curves. These are not guesses. They are supported by layers of independent evidence. We can even measure our motion relative to the faint radiation left over from the early universe, the cosmic microwave background. In that reference frame, our galaxy is moving at hundreds of kilometers per second. The radiation appears slightly warmer in the direction we are moving and slightly cooler in the opposite direction. That tiny temperature difference can be measured. So in one sense, we can define a cosmic rest frame relative to that background radiation. But here is the subtle point. That frame is not fundamental in the laws of physics. It is simply a convenient reference tied to the distribution of matter and radiation in the universe. The equations of motion, whether from Newtonian mechanics or Einstein's relativity, do not single out that frame as special. The laws work the same way in any inertial frame. This raises a profound question. Is there, at the deepest level, a preferred frame of reference? Or is all motion purely relative with no ultimate backdrop? So far, every experiment we have performed supports the relativity of inertial motion. We have looked for violations. We have searched for subtle anisotropies, directions in space that behave differently from others. We have tested whether the speed of light depends on Earth's motion through space. Again and again, the results agree with relativity, and yet physics is not finished. We do not yet have a complete theory that unifies general relativity, our theory of gravity, with quantum mechanics, which governs the microscopic world. There are proposals suggesting that space-time itself might have structure at extremely small scales. If that is true, it is conceivable that a deeper layer of physics could reveal something like a preferred frame. At present, we simply do not know. This is important because it shows the difference between confident knowledge and philosophical extrapolation. We know that within all tested regimes, constant velocity is undetectable internally. We know that acceleration has measurable effects. We know that motion is relative in every experiment performed so far. But whether this relativity is absolute and final is still an open question. Science advances by identifying what survives experimental challenge. The idea that there is no absolute rest frame has survived for over a century of increasingly precise tests. That gives us strong reason to trust it. Still, it is provisional. The humility built into physics is part of what makes it powerful. We do not claim that our current description is the last word. We claim only that it is the best model consistent with evidence. So when you sit quietly and feel stationary, you are not contradicting science. You are experiencing your local inertial frame, a perfectly valid perspective within a vast and dynamic universe. And the deeper structure beneath that perspective remains, at least in part, an open frontier. At this point, the physics is not the hardest part. The hardest part is psychological. Human intuition was not designed to understand orbital mechanics or space-time geometry. It was shaped by evolution to keep us upright, fed and alive within a narrow band of conditions on the surface of a planet. Our senses are tuned to immediate threats, sudden drops, sharp turns, unexpected impacts, changes in balance. We are exquisitely sensitive to acceleration because acceleration often signals danger. If the ground suddenly shifts beneath your feet, you need to react. If a predator lunges, you need to detect the rapid change in motion. But constant velocity offers no survival advantage to detect. If everything in your environment shares the same steady motion, there is nothing to respond to. So your nervous system simply ignores it. This is not a flaw. It is efficiency. The brain filters out what does not matter for action. It constructs a stable world from constantly shifting sensory input. The Earth's rotation, though enormous in scale, produces no rapid local changes in your immediate environment. The curvature of Earth's orbit around the Sun unfolds over months. The motion of the solar system through the Milky Way unfolds over hundreds of millions of years. These timescales are far outside the bandwidth of ordinary perception. There is also a deeper cognitive habit at work. We instinctively think in terms of objects moving against backgrounds. A bird flies across the sky. A car drives along a road. The background appears fixed. The object appears mobile. That structure is embedded in language itself. But when the background is also moving, and there is no larger visible stage behind it, the mind struggles. We want to ask, moving relative to what? And when the answer becomes relative to other moving systems, the chain feels unsatisfying. We crave a final anchor. Physics denies us that comfort. Instead of a single fixed stage, we have a network of frames of reference. Each one is internally consistent. Each one describes motion relative to something else. There is no universal stillness available to our senses. This creates tension between experience and theory. Experience says, I am at rest. Theory says, rest is relative. Both are correct within their domain. The difficulty is that our intuition expects one perspective to be absolutely real and the other to be merely apparent. But physics suggests that perspective itself is part of reality. The frame you inhabit shapes what you measure. When you look at the sky and see the sun rise and set, your senses present a geocentric description. From your frame, the sun moves. In a heliocentric description, the Earth rotates. Neither description is a hallucination. They are different coordinate choices applied to the same underlying events. Humans struggle because we are not naturally comfortable with coordinate choices. We want what is really happening, independent of viewpoint. But modern physics teaches that viewpoint is not an optional extra. It is built into measurement. So when you fail to feel the Earth racing through space, you are not missing something obvious. You are encountering the limits of a sensory system optimized for survival, not for cosmic truth. And recognizing that limitation is itself a step toward deeper understanding. Now we reach the part where the physics quietly turns into philosophy, not speculation, but careful reflection on what the physics implies. Right now, you feel stationary. Your body reports stability. The floor feels solid. The walls feel fixed. The horizon appears steady. Your internal sense of balance tells you that you are not moving. And yet, layered beneath that calm experience, you are participating in multiple simultaneous motions: Earth's rotation, Earth's orbit around the sun, the sun's orbit within the Milky Way, and the motion of that galaxy relative to others. None of these motions cancel. None of them are imaginary. They are all measurable. So what is stillness? Stillness, it turns out, is not the absence of motion. It is the absence of relative motion within your chosen frame. If everything around you shares the same velocity and nearly the same acceleration, then internally, nothing seems to change. And without change, there is no sensation of movement. This forces a subtle shift in how we think about reality. We often imagine the universe as a kind of stage objects move across it. Forces push them, and somewhere in the background there is an unmoving reference point. But modern physics suggests that there is no fixed stage separate from the actors. The stage and the actors are intertwined. Space-time itself is not a rigid backdrop. In general relativity, mass and energy influence the geometry of space-time. Motion and gravity are no longer separate ingredients layered on top of a static arena. They are part of the structure of the arena itself. When you stand on the Earth, you are not resting on an immovable platform in empty space. You are following a path, what physicists call a world line, through curved space-time. The Earth is tracing its own path. The Sun is tracing another. The galaxy another still. Your feeling of stillness is local. It is a property of your immediate space-time neighborhood. This realization changes how we interpret experience. The senses do not provide a complete map of reality. They provide a map of differences in pressure, light, acceleration, temperature. Uniform motion does not register because it produces no difference within the system. In that sense, motion is relational all the way down. And this has a quiet but profound implication. There is no privileged cosmic viewpoint from which the true motion of everything can be declared. There are only relationships between observers and events. The Earth is not secretly at rest somewhere. It is not secretly flying through a fixed void in a way that your body ought to feel. It is moving relative to other masses, other frames, other structures. That network of relations is what physics describes. So when you walk across a room and feel yourself moving, that sensation arises because you are changing position relative to the floor, the walls, the air. When you sit still and feel no motion, that is because those relations are not changing in your local frame. The deeper insight is that reality is not built from absolute positions and velocities. It is built from relationships. You are not a stationary object in a moving universe. You are part of a continuously evolving web of motion in which stillness is simply a special case, a moment where, locally, nothing changes. And once you see that, the ordinary feeling of standing still becomes something more subtle, not a contradiction of cosmic motion, but an expression of how motion itself truly works.